Previously, we've defined work being equal to the force F applied in the direction of the displacement multiplied by the displacement x. But we know that force is defined as the product of mass and its acceleration. And acceleration is defined as the rate of change in velocity, that is, the difference between the final velocity and the initial velocity divided by the time taken. We also know that the displacement is equal to the average velocity multiplied by the time traveled at this velocity. Average velocity is equal to the final velocity plus the initial velocity divided by 2. When we expand out the brackets in this formula, we get a formula for work that is half of the mass times the square of the final velocity minus half of the mass times the square of the initial velocity. The term half mv squared is called the translational kinetic energy. It has the same unit as work, that is, Newton meters or the joule. As the formula shows, kinetic energy is the energy associated with motion. If a mass is not moving, then it has no kinetic energy. If the mass is moving very fast, then it has lots of kinetic energy. Work then is defined as the final kinetic energy minus the initial kinetic energy, or the change in kinetic energy. If the final kinetic energy of a mass is greater than its initial kinetic energy, then the quantity work is positive, and we say that the work has been done on the mass and the mass gains energy. For example, an engine in a car can do work on the car to accelerate it from rest at a stop sign to some speed. It increases its kinetic energy as it speeds up. If the final kinetic energy of a mass is less than its initial kinetic energy, then the quantity work is negative, and we say that work has been done by the mass and the mass loses energy. For example, a moving car can do work on a brick wall and knock it down if it collides with that wall. In the process, it loses its energy and comes to a stop. Now let's have a look at an example. Consider the Lamborghini Huracan, which has a mass of 1,500 kilograms, including the driver. How much work is required to accelerate the car from 60 km per hour to 100 km per hour? To answer the question, we need to determine what the kinetic energy before and after is. The work done is this change in the kinetic energy. So the initial kinetic energy is equal to half of the product of the mass and the square of the initial velocity. The initial velocity is 60 km per hour. So what's the initial velocity in SI units? The initial velocity in SI units is 16.7 meters per second. So what's the initial kinetic energy given that the total mass is 1,500 kilograms? The initial kinetic energy of the car and its driver is 2.09 by 10 to the 5 joules. Now for the final kinetic energy. The final velocity is 100 km per hour. What is it in SI units? The final velocity in SI units is 27.8 meters per second. So what is the final kinetic energy given that the total mass is 1,500 kilograms? The final kinetic energy of the car and its driver is 5.80 by 10 to the 5 joules. So the work done to accelerate the car from 60 km per hour to 100 km per hour is the difference between the final kinetic energy and the initial kinetic energy. So what is the work done? So 3.71 by 10 to the 5 joules of work was done to accelerate the car and its driver from 60 km per hour to 100 km per hour. In summary, translational kinetic energy is defined as half of the product of the mass and the square of the velocity of the mass. Work is the difference between the final kinetic energy and the initial kinetic energy. When work is positive, then work has been done on the mass and the mass gains energy. When work is negative, then work has been done by the mass and the mass loses energy.